Okay, now make the last two comments about derivative business. I'll come back to it a little later after I move to the functionals on this kind of spaces. You can see how to measure them. Now, the thing that I had was that if you want to prove the fundamental theorem, finally it boils down to two steps. One is how to do it for non-negative functions. And from there we get what is it that finally we want from non-decreasing function. So suppose f is less than 0, f is integral, then fx is equal to all this in a to x, fx dx, then okay, we are investigating whether the integral of the f prime is fb minus fp. That's exactly what our f prime is. F prime is equal to fx almost. So is prime is equal to f prime. Now the question is, suppose we know that f prime x is also one, so I don't know what one it is. So we need to set up all x, let's have f prime x. Let's keep that. That's it. So the measure of the complement is 0. Now, if f is non-negative, you can define fn to be the function fx if 0 less than or fx less than l and equal to l if fx. This is the usual. You follow the function up to some level and then come. So then we know that fn x now you look at this fx. I'll write it as all these fnx are nice fellows. They are bounded functions. Okay. Let's call this as gnx and this is fnx and this is. Now, what are the things that we know? Fnx is differentiable almost everywhere and fn prime x equal to fnx because of our theorem for bounded measurable functions. We had this one because fn bounded. Secondly, if you look at gnx, since fnx increases to fx, fx is always greater than or equal to fnx, so it's a non-negative quantity. As you increase x, you get more value. So as a function of x, it is not decreasing function. For each fixed n, gnx is not decreasing as a function of x. And therefore, gn prime exists and greater than not decreasing function. So whenever the derivative exists, there it is. All these are. Therefore, if I now come here, I can take f prime x is equal to gn prime x plus f prime x. Where? At all the points where this makes sense, at all the points where this makes sense, at all the points, so at the point where all these three make sense. Okay. Now this does not make sense at a set of measure 0. This does not make sense at a set of measure 0. This does not make sense at a set of measure 0. Throw away 3 sets of measure 0. You still got, you have thrown away only a set of measure 0. So this holds almost everything. Okay. So this holds except that those points where a prime, df prime, fl prime don't make sense, and this is of matters. Now gn prime is greater than or equal to 0. So by 2 this is greater than or equal to 0. Because gn prime exists. And for every n we can do this. True for all n. But what is fn prime? What is fn prime x? So all these are almost everywhere. All those sets of measure 0 at each stage I throw away, and only a finite number of them I throw away. Therefore, you have throw only a finite number of them. Here, I have to throw away all those points where, first of all, fn x. All those points where fn prime x is equal to fn x. Other points I have to throw away. And I have to do it for each n. So I will be throwing away a countable number of sets which are of measure 0. And it is still of measure 0. Because by countable subordinate. Mu of u union is less than or equal to mu n, but each one of them is 0. So here I have to do it for each n. So for each n I am throwing away a set of measure 0, but only a countable number of them, and so I am throwing away eventually a set of measure 0. So this is less than or equal to almost everywhere for every n. And fn converges to f, therefore f prime x greater than or equal to. Okay, what does that tell us? That only says that. Suppose we can show a lemma. I don't know what that lemma should be. Integral a to b f prime x dx is also less than or equal to b. Suppose we can show this lemma. Right? Then what happens? I have integral a to b f prime x dx. It is greater than or equal to, it is less than or equal to, therefore it is equal to fp minus fa, but fp minus fa by definition a to b fx dx, and that says a to b, all these are finite because of integrability coefficient we have. That's equal to 0. We are done. Why? Because f prime x is greater than or equal to fx. You are integrating a non-negative quantity, and the total integral to 0, you don't know if the function is 0 almost everywhere. If it were non-zero on a set of positive measure, that part alone would have contributed a positive quantity to the integral, and therefore this implies f prime x is equal to f prime almost everywhere because f prime x minus f prime is equal to f prime, and we also get that the integral a to b f prime x dx is equal to fb minus fp. So that is the fundamental theorem. So what was the finally clinch? That we have to get. That's all there is to it. In the whole proof, finally it boils down to showing this is the thing that we have to see whether integral f prime x dx is less than or equal to f. And what are the things that I know about f prime? F prime is the derivative of a non-decreasing function because little fx is non-negative. As you increase x, the integral increases, so fx increases, so f prime is the derivative of a non-decreasing function. So the lemma that we have to show is, if I have a non-decreasing function, the integral of the derivative is less than or equal to the fb minus. So all we have to prove is fx is non-decreasing function then or let me call it g so that I don't confuse it with those. Then I will apply this result with g as capital F. Okay. All you have to do is apply with g as capital F and you get that. So this is the main lemma. And that's not it. Finally it boils down to where is it all lying? The main thing that is for non-decreasing function. I don't even, in fact, I will not get equality in general. For example, let us take a, b, take this midpoint. Okay. Take the function to be 0 up to this and 1 after that. It's a non-decreasing function, right? What is f prime x, gx is equal to chi of 0 if a plus 2 and 1 if a plus 3 by 2 plus 1. Suppose I have such a function. The derivative exists almost everywhere except at this point the derivative exists. Here it's constant, so g prime x is 0 here. Again here it is constant, g prime x is 0 here. So g prime x is equal to 0 or not. Right? What is integral g prime x? 0. But what is gb minus gx? 1. It is 1. So here I have integral a to b g prime x dx is strictly less than 1. So what I am saying is that strict inequality can take place. So we will say that's all it takes. Either strict inequality or equality. So g prime x dx is less than or equal to gb minus gx for a non-decreasing. That's what the main is. And if we have that, we are through with that whole chapter on fundamental theory of integral calculus. Now here again I'll just indicate the proof. So you know g prime x exists almost everywhere. So let us again take E to be set of all x where g prime x exists. Now take any point in E. We know that g prime x exists there. So we have to worry only about those points where the derivative exists because the integral, the other part is irrelevant. This is a set of measure 0. So we have to worry only about the point where the derivative exists. Take the point x in any point x in E. So we know that G prime X exists. That says the standard trick will convert to what? As G prime X and then test. Let's call this as G and X. Okay. So G and X tends to Gx almost everywhere, because at every point of X this will happen. So G and X tends to Gx almost everywhere. What else can I say about G and X? G is non-decreasing, so this will be more than that. Gx plus 1 over n at a later point will be more than the earlier point. So G and X is greater than or equal to G and Y. G and X is greater than or equal to 0 because G is non-decreasing. And whenever I have a sequence of non-negative functions, if the integral converges, then I have some theorem. I can ask whether the limit of the integral is the integral of the limit. But I don't know whether the integrals of the Gn converge. So whenever I don't have convergence, the only thing I have the Father's lemma. Now what does the Father's lemma say? When you have non-negative functions and which converges to something almost everywhere, what direction does it go? In of integral, I never remember the direction, is greater than or equal to 0. Right? Now, let me write that. So that says lim min A to B here. But what is this? Since Gn converges to G prime, lim min is the same as the limit. So it is A to B. Right? So we have this integral A to B B prime x less than or equal to lim min A to B. Right? But what did we want? We want G prime to be less than or equal to G min. So it's enough. Lim min of integral A to B is okay, and we are done. So now I will just write the steps and do one or two things to think about it. I will have to just explicitly write what that is. So proof of this. Integral lim min Gn dx is equal to lim min A to B. What is Gn? By definition, Gn is that. So now we split this. Lim min A to B Gx plus 1 over n. Again, I check Gx. This trick we have done before. Here change of variables, Wheeler-Berg integral is translation invariant. So that is A plus 1 over n, B plus 1 over n, dx dx minus A to B dx dx n times is equal to lim min. I can rewrite this as n times B to B plus 1 over n dx dx minus n times A to A plus 1 over n. This trick also we have done. That is equal to lim min n times B to B plus 1 over n dx dx plus lim min minus n times use the now this is the step. This is equal to GB and this will give you less than or equal to minus. So if you use the non-decreasing nature of G, you can conclude that this is actually equal to GB. Now, roughly, what does that first term? Let's look at second. First of all, A to A plus 1 over n affect the gx dx. Now, G is not decreasing. So, the smallest value is Ga. So, that is greater than or equal to Ga times 1 over n. So, n times this is greater than or equal to G. Right? And therefore, minus n times that is less than minus G. And this is true for every n, therefore the limit is less than or equal to G minus G. So, true for all n, for every n. Therefore, the limit of this is less than or equal to minus G. So, that part is taken care of. Okay, the second term is less than or equal to minus G. Now, only thing is the first term. I will just point out there. The first term, again the same trick. The smallest value is GB. GB into 1 over n. Into n. GB into 1 over n to n. So it is GB. The largest value is GB plus 1 over n. The highest value is B plus 1 over n times n and the goal. So this integral second term lies the square v n. And from that you conclude that the limit is indeed equal to GB. Okay. From that you conclude the limit is indeed equal to G. Greater than or equal to that, I will be M goes keep coming down, conclude with this. So therefore we are. So we have the fundamental theorem modulo one fact which I have not yet proved, which I will come back a little later. That first of all, for a non-decreasing function, the derivative exists almost everywhere. With that assumption, we have proceeded everything we have been able to successfully get. So modulo the fact that requires something called Vittal theorem. I will come back later to that. We will spend enough time. So modulo that statement that a monotone non-decreasing function is differentiable almost everywhere. We have the fundamental theorem of integral calculus, which uses all that. So we have the function which is integral, then its indefinite integral is a differentiable function and it can be recovered by integrating it there.
So what's the difference between that and first term and the second term?
Correctly?
There's an inequality there, but here you're saying it's equal.
That's right. Because why? Actually, you see how we can sharpen it. I did it quickly. Okay. I did it very quickly and got what I want, GB minus. There may be a sharper way of doing it. Okay. The end result is that I want to get GB minus G. Here I got that GA very quickly without having to worry about this thing. But here I have to, I don't get that GB so easily. Because of the minus sign, there I wanted the lowest value. Here because of that I want to go to the highest value. There the n was not there, right? Therefore straight away I will get the GA. So I will get a GB plus 1. If I have to dominate that, I have to go to the highest value. So it will bring in a GB plus 1 over m. But I want a GB. Then I observe this and then calculate the unit. You understand? Here because of the minus sign, I need the lowest value. Yeah.
Speaking, should we be writing integral over E d dash of 7? Because it is defined only on E.
Yeah, but the other set is a measured 0.
But what would that be?
It's called is still 0. See, integral, suppose E equal to E1 union E2, E1 and E2 disjoint, then suppose any x, the integral over x is equal to integral E1 plus integral E2. Right, therefore now we have integral A to B is integral over E plus integral over E complement. The integral over E complement is whatever be that I define to be, I can define that to be any chunk.
So we have to modify
Modify
take it as modification of
Yeah, naturally, it's an extension. To define it anyway, you want as some real number, but since the measure is 0, that the integral will always be 0. That's the. So the integral over E or over any set or measurable set A of a function f which is 0, f is equal to 0 or okay, let me not write is equal to 0 to measure of A. If you take a set with measure 0, to integrate anything you will get only 0 because that set has no mass.
So then that G dash actually is not G dash, it's something else.
Yeah, what I want to say is that integral A to B G dash x when I say, which is the same as integral E G dash. I define it this way. The other part I don't know what it is. You take it to be anything you want. It may not be the derivative, but it's an extension of that function. Any extension will give the same result. That's why it doesn't matter what you do.
Because we have substituted at A and B as we go through the proof. I just worried about.
But G is defined.
G is defined.
G is defined. That's why I like G.
For that.
Where I have substituted for G prime. I have not substituted for G prime anywhere. I have substituted only for G. G is defined in here. G is a non-decreasing real valued function on A. G is well defined. That's fine.
So that will not be G actually. That G of x plus 1 by n minus G of x by 1 by n going to G dash x.
Where here?
Yeah.
Yeah.
Because G dash x is modified.
It's almost everywhere. Only on E. So it converges almost everywhere. And for Wathu's lemma, almost everywhere converges. Again. Whatever you modify, the convergence failure is only on a set of measure 0. Again, that's gone. So the sets of measure 0, moral of the story is sets of measure 0, you don't worry in integration. Your definition?
Direct delta function and all that will also be only at measure 0.
Yeah, but then that is not Lebesgue integral. That's the thing. Okay. But we write it as though it is a Lebesgue integral. That is not Lebesgue integral. Okay. There, you are trying to give all the mass to one point, 0. So that's a different measure altogether. So delta is more a measure than a function. When you say integral fx delta x, what you are really meaning is I am integrating f with respect to the measure, delta measure, which gives the mass only to that one point. So I can integrate over that point and its complement, and its complement is measure 0, it's all gone. The integral over this is simply the value at that point in the measure of that set, which is 1. So that is how you get it. So when this Dirac delta has to be interpreted as a measure, but a measure has to be interpreted as a functional, and therefore the Dirac delta has to be interpreted as a functional rather than a function. Well, every functional is also a function, but only you have to be careful about the domain and the codomain. Where is your domain of definition of the function and where is the codomain? When you are talking about f of x, your domain of definition is the set x and codomain is R. But when you are talking about delta, the codomain is still R, but the domain of definition of the function is a collection of functions. It is not just R. That is where the difference is.
So it's more of a definition for delta.
Yeah, delta requires, what we do is a loose thing. What we are doing is a loose thing. So what we are saying is, we are using, actually we should write d delta. It is some atomic measure, and I am integrating with respect to the atomic measure. And we pretend that there is a density function for this measure, and it can be written as some function delta x dx. And that's where the whole problem.
Sir, but when they define delta functions as limits of distribution functions,
That's a different story.
then it comes to
Then you are talking about a measure as a limit of a sequence of measure. And there again a whole story of convergence. What is the sense in which it converges? There is a book by Billingsley. It talks only about convergences on various senses of measures. Okay, there is a huge lot of that Billingsley is the master of. Most of the work is due to him. You have a book on only convergence of measures. So it has to be interpreted in the sense of convergence of measure. Now what I said was every L1 function defines a measure, and now that delta I is to be approached through the sequences of measures generated by L1 functions, but the limiting measure is not generated by an L1 function. That's where the problem. But all that confusion is gone. You clearly say that it is also a function, but only thing is it's a function defined on not as a domain or an interval, but its domain is a set of functions. So you have a set of functions and you have real numbers, and delta is a map, that is it associates a number with each function. Our normal functions, normal and abnormal, with each number it associates a number. The delta with each function it associates a number, and it has certain reasonable convergent properties. If I have a sequence of elements here which converge, that means I have a sequence of functions which is converging in some sense, then the corresponding values will also converge there. That is the sort of continuity we are asking for.
and the value is the value at 0.
Yes. Well, you could have taken shifted also. If I have delta 8 and then f of my t minus a wherever. And depends on where this collection of functions are defined. So depending on that you will evaluate. So therefore, Lebesgue is still not enough. Lebesgue's integration is just not enough. So that is why finally integration is interpreted as a linear functional, and if you interpret it that way, finally you can give the meaning of delta as an integral in that sense of functionals rather than anything. Because every linear integral has to be interpreted as a linear function.
So in that sense, it can be something like fundamental theorem.
I didn't get that.
The integral as a function as well. In that sense, is there something parallel as fundamental theorem of calculus?
Yeah. Definitely there is something called the derivative of this. In fact, there the story becomes much easier. Every distribution is differentiable any number of times. So the delta function can be, in that sense, can be differentiated any number of times, and all kinds of funny things happen. Okay. Very easy things happen which are parallel to what is happening here. Yeah. The whole theory of distribution comes out with all these things. You can do all that. Yes. See, whereas we struggle so much about differentiation when we are having these functions in the normal sense that we are used to, but when we interpret these distributions, these functionals like the delta, when we give that correct meaning as acting on a class of functionals and all, there is a nice way of defining the derivatives based on our experience with what happened in the normal situation. And that makes the story so easy that I can now go on differentiating these fellows any number of times. All the problem about differentiation and the thing goes away for these distributions. Maybe I should do a little bit things about distributions sometimes. Okay, once I finish L1 and L2 or L3 functions, then. The basic idea is the following. We take a collection of functions and then we have an association with each function, some number. A natural guy associate the value of the, like a filter. You filter out all the values and just see the value at the point f of 0. So everything else is fudged out. Only the point 0, you see the function absolutely clearly without the other values disturbing it. And that's what the delta function is. You are actually filtering one particular information instant of that function. Okay? That is what the delta function is. So it says that if I had a wave like this, if I look at it, it's very confusing. So what I do is, I'll simply filter out all these things and my filter will simply put the output that particular number fc. That's all. That is what the delta function does. And what we do is, loosely, if I now have the information to filter at each point, then I can put them all together and get the function. That's where the delta integral, loose integral comes in. So we simply say fx delta fy delta y minus x. If I integrate it over all the y's, I will get fx. That's sort of very, I have the filtered value at each point, so therefore I know the function. So these are all funny little things that take place, but they all have a proper formal meaning, correct mathematical interpretations this is called the Schwartz distribution, Laurent-Schwartz distribution. It's all motivated in what is going to happen now. We will see slowly, okay? The whole functional theory on LP space is developed. From that we get all the ideas of how to handle it. It was all there. We were just not seeing it properly. The question is, it is all ordered. That is why we call it research. It is all there. It is not something you have discovered. You are searching, it is already there. It is research. Okay. It was there. It was probably some, even we are giving the credit that somebody else knew it, but he didn't tell me, so I am researching it. Okay. It's all there. But only thing is we are not seeing it properly. If you see properly, so for everything there is a mantra. You utter that mantra, then you see it clearly. And the mantra to interpret the delta is the Schwartz thesis. So it was a thesis by Schwartz. Probably 1950. Yes. Okay, where was that? So the derivative has a lot, but we'll keep going and then we'll keep coming back to this again and again. The next thing I want to look at is the so-called LPGs. I will first start with what we mean by this, and then we'll slowly get into. So suppose now I can do it in a general measure, whether I do it on the real line or the general measure, it is the same, because now I have notion of measure, we have notion of simple functions, then integrals, everything has now been properly defined and everything is there. So if you don't like it, you take it as real. Suppose I have a set omega and a sigma algebra and a measure of that. Okay, omega being mu. So if you don't like it, take omega to be R, B to be the Lebesgue measurable set, mu to be the Lebesgue measure. That's a model. Take any set omega, or if you are familiar with probability theory, take omega to be the sample space, B to be the sigma algebra of events, mu to be the corresponding probability measure. But then you are in an advantageous situation there because you have a finite measure. Now I am looking at what people have in general also. So suppose I have a measure. Now when you want to integrate, I said that any two functions which agree almost everywhere, they are the same integral. Okay, so from the point of view of integration, I must treat two functions which are equal almost everywhere as the same functions. There are no difference between them, they are going to give the same result. So in other words, there is an equivalence relation defined. F is equivalent to G, if F is equal to G almost everywhere. Okay. So F is equal, we say F mapping omega to R, G omega to R, we say is equivalent to G if F equal to plus. Now we have already preempted by saying it's an equivalence relation. Okay, so let's take first of all, what do I mean by that? Let F be n be the set of all measurable functions, mu measurable. Now, whenever I say the measurability will be with respect to the measure, mu measurable functions are only mu measurable real value. So then in that class, if Fg belongs to F, then we say F is equivalent to G, F is equal to G almost everywhere, and we have preempted the fact that this is an equivalence relation on F by using that notation. Well, that's very clear because F is equal to F almost everywhere, but everywhere. So F is equal to F, F is equivalent to F. If F is equivalent to G and G is equivalent to H, what happens? Implies F is equal to G almost everywhere. G is equivalent to H implies G is equal to H almost everywhere. Now I want to conclude F is equal to G, H almost everywhere. Throw away this set where F and G don't agree. Throw away the set where G and H don't agree. The remaining part, everything else agrees. So it implies F is equal to F. This is the transitivity. And if F is equal to G almost everywhere, G is equal to F almost everywhere. So symmetry is also there. So it's automatically an equivalence relation. So this is just to sort of formalize this thing. Then whenever you have an equivalence relation on a set, it immediately introduces a partition. And what are those partitions? The equivalence classes are the parts. Each equivalence class will be a part. So what do we say? If F belongs to F, we denote by, let's use this notation. The equivalence class generated by F. This is a typical thing that mathematics always does. Whenever there is equivalence class, reduce the size by putting all the. What is this equivalence class generated by F? It is the set of all functions measurable such that G is equivalent. All those fellows which are equivalent to F. That means all those functions which are equal to F almost everywhere. All those functions which are equal to F almost everywhere. Well, there was one function which is equal to F in this set with measures of that 0. There will be another function which is equal to F except here measure of that 0. But what we are saying is every function agrees with F except on a set of measures 0. So this is called the equivalence class generated by F. Now what do we know by this what do we know that about these equivalence classes? If G1, G2 belongs to F, then G1 is but because G1 is equivalent to F and F is equivalent to G2, therefore G1 is equivalent to. So all the fellows in that box are equivalent to each other and equivalent to F. Then F belongs to the equivalence class. Obviously, because F is equivalent to it. The important thing is, if you take two equivalence classes, one generated by F and another generated by G. One more point I made is all in partial equivalence relation, so I will quickly go through this. Suppose I take an element in the equivalence class generated by F. Then look at the equivalence class generated by G. That will be exactly equal to the equivalence class generated by F. So what it says is, you can randomly pick anybody from that box and take him as the representative from that box. You are not going to lose anything in the integration. Every fellow in that box generates the same box. So any fellow in that box is a good representative of that box. And most of the time in equivalence relations in mathematics is with respect to certain property, generate this equivalence class, put all the elements in different boxes, then one representative in that box will tell you everything about that box. What is the right representative of each box? That is what is generally called canonical form, normal form, etc. etc. What is the correct representative? In the sense, who has the simplest form, which reveals all the properties just like that. Okay, that is what all the study about canonical form, normal forms, etc. But let's look at this now. And next property is, if you take two elements and look at the equivalence classes generated by these two elements, either this is equal to empty, that is, they may not have anything common, or that is not common, means that is non-empty. These are the two possibilities. Now what happens in this case? This means there exists an H which belongs to F and H belongs to G, because there is a fellow who is common to both of them. But since this belongs to F, the equivalence class generated by him must be the same as F. If take somebody from that box and look at the box generated by him is the same box. Similarly, since he belongs to here, so that says F is. So what this says is, if you peep into two boxes, they are totally identical or completely different. They are totally disjoint and everything is common. So any two equivalence classes are disjoint or completely identical. Now what we do is, therefore, we take the distinct equivalence classes. Take all the distinct equivalence classes, they are all disjoint. Because no two distinct equivalence class. Distinct means what? They have nothing in common. Two distinct equivalence classes, and take all of them, and that is what is known as actually the quotient of F under this equivalence. So we will call this F the collection of all. Actually, therefore, we are always looking at equivalence classes of functions. But then what we do is loosely we take one representative for each fellow and work with him. That's all it boils down.
So in Cantor construction, we are considered the equivalence class of Cauchy sequence.
Pardon me?
Equivalence class of Cauchy sequences.
That is the Cauchy construction of the real number. Yes, right.
Is it called the Cantor construction?
It is the Cauchy construction, not Cantor's construction.
Okay, so we have talked about the forms.
There we do. What do we do? We take all sequences of rational numbers.
Yeah.
Okay? And then we define an equivalence class there.
Yes.
With respect to that equivalence class, all the sequences are divided into a number of boxes.
Yeah.
Each box is a real number.
Okay, and what about, you are talking about the right candidates from each box, right? Which has the symbols.
Yes.
Those.
There the problem is more different. If it is a rational box, one rational number is the RRR, a constant sequence is the best representative of that box. But in the other ones, you are your own creations. The real and the non-rational numbers, the irrational numbers are your own creation. So there are many sequences which will represent, which are good representatives of the thing. There is nothing like them. But suppose you take all matrices, n by n matrices. You say a matrix A is similar. You see, we use the word equivalent in many terminologies. A is similar to B. If P inverse A, P is equal to B. Now take the collection of all the matrices. Similarity is an equivalence relation. Quotient them. You get a number of boxes. What is the correct representative? This is called the Jordan form. The correct fellow who has either all diagonal and others zero, or all diagonal and subdiagonal is non-zero, 1 or 0. So that is the correct canonical. That is the best Vishwarupa of each box.
So the problem with the real number construction is in order to get the completeness
We have done that.
we are done.
There our aim was topological.
Okay.
There our aim was not getting a good form. We wanted to, there was some defect, we want to create. We created it. Now here what we are doing is already there, but now I want to study it. In the collection of all distinct equivalence classes, so that we denote by F tilde. So now, from now on, when I say F belongs to F, I really don't mean F, I am looking at an F belonging to F, I am looking at the entire equivalence class belonging to F and taking little f to be the representative of that. That's all. Okay. So what is the meaning of LP space? If the integral of peak power is fine. So what I am doing here again, if you take any other function which is equal to this almost everywhere, that will also give the same number, that will also have the integral finite, that's all. One fellow is in having peak power finite integral, all the other fellows in that box will have the same integral value and therefore will also have finite. So whenever there is a tacit understanding that whenever I say this, it is up to almost everywhere equivalent. This is all defined. Okay. So we say that F belongs to LP if this happens.
So what was capital F?
What do you mean?
What was capital F?
Capital F is the collection of all real values new variables dependent or new variable functions dependent. So you take functions from omega to r, think of random variables. If omega is in a sample space, you are thinking of all the random variables.
Sir, here the integral is again that simple functions less than.
Yeah, that's same story.
Same.
That has to be
Then the
complete.
supremum of
That's what that is what is meant by Lebesgue integral. All these are Lebesgue integrals. So whenever this is finite, we look at, we say that F belongs to LP. Now I have not said anything about P, so let's take the time being, let us take 0 less than P less than infinity. When it is equal to infinity, we don't know. The time being, you can always, if some number P is given, you can take that P power and take. Of course, there is a, suppose P is root 2. Okay? And at a point x, mod fx was root 3. What is mod fx to the power of p? What is meant by this? Root 3 to the power of root 2. How do you interpret this? It's a number. What is that number? How do I have to interpret this?
that make sequence is going to root 2 and
See, the problem is eventually first you have to introduce the exponential e. Okay, and then divide it with the e to the power of root 2 log. So the calculus is not, I mean, it's all not, you have to introduce the exponential function, okay, and then look at its inverse, that's a monotone function, it has an inverse function, and that is a logarithmic function. Once the exponential and logarithmic functions are defined, this is to be defined a to the power of b has to be defined as e to the power of b log a. Now since I want to define log a better be positive. Because log a in the real situation is not defined if a is not positive. So a to the power of b is defined only if a is positive. Okay, that is called the base. And b can be any real number. It has to be so a is positive, a to the power of has to be defined as e to the power of b log a. That is the definition. I remember, I'm letting out a secret because anything is declassified after a certain number of years. So this happened about 37 years back, so it can be declassified. I attended an interview for a faculty position at the institute. Professor Dhawan was the director at the time, was sitting in the chair, and there are other members of the committee. Then Dhawan asked me, how do you define root 2 to the power of root 3? I said, how I define will depend on what is your knowledge. Then he said, assume that I don't know anything. Then I said, I will start with the definition of real numbers. Will you give me enough time? No, assume that I know calculus. Then I asked him, do you know exponential? E to the x. He said, yes, I know e to the x. I said, what is e to the x? Then he said, are you interviewing me or am I interviewing you? Because I had to answer you, I should know what you know. Then only I have to start from there. Then I asked him, you know what is e to the x? It is that. No, that is not mathematics. That is handwriting. Do you know what is e to the x? He said, I don't know e to the x. You tell me. Then do you see the property? Do you know that it is monotone increasing? Yes. Do you know that monotone increasing functions have an inverse function? Yes. So slowly, good. Okay. Now I got the law. Once I have this and this is the definition. Then, Alan said, I had asked this question to all the previous candidates. The only answer they gave me was multiply root 2 times with each other. Faculty person. But then, he said, this is the first time I understood what is a to the power of b. There is a lot, that's what he said, there is a lot of things that are involved we take for granted. And then somebody in that expert committee said, no, you don't need all that to define root 3 to the power of root 2. Prof. Dhawan was an extremely clever person. He understood by the time the subtleties involved in this. He simply turned at him. Even now, if you have not understood what is root 3 to the power of root 3, I am sorry. So there is a lot of subtleties involved in this definition. And
Even we know how to calculate something to the power of rational.
Yes.
Then we could also define that as 3 power half and then a sequence.
Then again limiting process here. That will come back to how do I define root 3 to the power of 1 over n.
Yeah.
Suppose I put a 1 over root to that. It will be even more difficult. So there is a lot of problems involved. So we first define exponential functions. The standard exponential function e to the x, and then the general exponential function a to the x is e to the x log a, and then you are through everything else. That is the correct way of defining. In fact, there is much more subtlety involved. Remember, how do you define e? How do you define e?
1 plus 1 by n 4 to the power of
1 plus 1 by n
4 to the power of n as n tends to infinity, or 1 plus epsilon 4 to the power of n.
Okay, suppose this definition. That's a number. Okay? Then what is e to the x? How do you define e to the x?
1 plus x square.
1 plus
Square.
plus x plus you show that this infinite series converges and converges uniformly on complex, all kinds of nonsensical theorems we prove, and finally that function is called e to the x. Okay. Now what is the connection between this fellow and that fellow? That is also a this fellow constant. Now what is meant by this? What is that? It is again e. 1 plus 1 over. So there is some connection. So in other words, what God saying, if I raise this series to power x, I must get this. What is the meaning of all this? All that has to be tested. There is a lot of things that are very subtle questions that has to be settled, but we take for granted all these things are there. Okay? So in general, therefore, the mathematician is not at all happy with anything. Whatever you give him, he is not sure this is right or wrong. There is some logic missing in it. What is the connection? Okay, anyway, now we know what is meant by the integral. Okay. So we have this LP, the so-called LP, okay, where all these fellows are. When the integral is finite, peak power integral is finite, we call it as a LP function. Now suppose fx is real value, okay, all these are, capital F the real value of the real value. Now suppose I have two functions f and g. I will not write omega mu all the time. So we have fixed that measure space. Now we are considering everything with respect to that space and that measure. Suppose I have two functions in LP. Then what happens is mod of x is a real number. Mod gx is a real number. Therefore, when I have given me two real numbers, I can define the maximum of these two. For two real numbers, the maximum of these two real numbers, call it mx. Now, what can I say about mod fx plus mod gx? That is less than or equal to mod fx plus mod gx for any x, right? But mod fx is less than or equal to mx, mod gx is also less than or equal to mx, so it is twice mx. Mx is now non-negative, I don't have to put a modulus for that. It is the maximum of fx and gx, so anybody is less than or equal to the maximum. And therefore, mod fx plus gx to the power of p is less than or 2 to the power of p mx. Now, mx to the power of p may be mod fx to the power of p at one point, at another point it may be mod gx to the power of p, depending on at that point which is maximum. So, to avoid that, what I do is I put both of them. Right? So, this will be either this or this. At any rate, I have added something extra, so that it will be less than or equal to mod fx to the power of p plus mod gx. Now therefore, integral of this is less than or equal to 2 to the power of p integral of this plus the integral of this. And both are finite. Why? Because f is in LP, g is in LP. Therefore, f plus fg in LP implies f plus g in LP. So this collection of P LP functions are closed under addition. Now clearly f belongs to LP implies alpha f belongs to LP for every other. Why? Because I want to integrate alpha x to the power of p, only alpha to the power of p will come out. The rest of it is finite anyway. So therefore, LP is a vector space. Well, I put therefore, but the rest of it is obvious. With the collection of all functions of a vector space, so any subspace closed under addition, scalar multiplication, right? Or verify the zero function. What is the zero function? The function which is equal to zero almost everywhere. Okay, everything is in terms of almost everywhere. Negative function is there, and then everything in the multiplication distribution. So there is no problem. LP is a vector. Now I am going to look at one simple property. Which will all be put together later. It will all be used here. Suppose I take two such indices, P and Q. Okay. Now suppose F is in LP. Suppose F is in LP. Okay. What does that mean? Integral mod F to the power of Q E mu is finite, integral over omega is finite. That's what is meant by saying F is in LP. Now for any x, look at mod fx. It is either less than 1 or greater than 1, greater than equal, greater than equal. Either less than 1 or greater than 1. If it is less than 1, what happens to mod fx to the power of p? If I take a number which is less than 1 and take any power, it will be still less than 1. Whether the power is more than 1 power or less than 1 power. If you take 0.5, if you take the square of it, it is 0.25. If you take the square root of it, it is still less than 1. Because if you take two numbers that are greater than 1 and multiply itself, if you take a number greater than 1 and multiply it itself, the square will become bigger than 1. So therefore, whatever be, the pith power will be less than. But if it is greater than or equal to 1, then when I take the pith power and I take the qth power, which will be more? Qth power. Q is more than P, so the qth power will be more. So whether it is less than 1, this holds, greater than 1, this holds. So what I will do is I want to put 1 inequality for both. Therefore, mod fx to the power of P is less than or equal to 1 plus mod fx to the power of Q. See, when if it is less than 1, this term itself takes care of it. When it is greater than 1, that term takes care of it, something addition is there. So thereby, by combining these two, I dominated mod fx to the power of p by one single quantity. And therefore, integral mod fx to the power of p d mu over omega will be less than or equal to integral d mu plus right? Now, this is finite. Suppose this is finite, then this will also be finite. So that means F will also be in LP. So if F is in LQ, F is in LP, provided I assume this is finite. But what is this? This is the mu of omega. So if we have a finite measure space, if F is in LQ, it will be in LP for all smaller p's. Whenever you belong to some L of some power, for all smaller powers it will belong to L of that power. So therefore, if this is less than infinity, if mu of omega is less. So what is the conclusion? Therefore, omega b mu, the finite measure space, then F belongs to LP, LQ implies f belongs to LP if P is less than. If P is less than 2. Now for example, if f belongs to L2 of 0 to 5, that will imply f belongs to L1 0 to 5, right? Because finite measure space, so whenever it belongs to some higher L, it will belong to that lower L also. P is less than Q. Now this is what is happening in Fourier series. All the Fourier coefficients are well defined, but the function is in L1, and therefore if it is automatically well defined for functions in L2. If the function is in L2, it is automatically in L1, and therefore the Fourier coefficients are well defined. So therefore, there is, once you define the Fourier coefficients for periodic functions for L1 function, automatically you are taking care of L2, L3, whatever you want, particularly the finite elements, the Fourier series will get defined. But this is not so if the measure is infinite. Suppose mu omega is infinity. Let's take for example omega to be 1 infinity, infinite measure, Lebesgue measure, okay? The measure required is the Lebesgue measure. Then look at this function f of x to be FBC. Let's say what the x to the power of 3 by 4. Well defined, okay? Because the 0 is nowhere in the picture. Denominator is also. Then what is non-negative? So modulus is not at all. What is integral of that is dx by x to the power of 3 by 2. What is that integral? X to the power of minus half from 1 to infinity, and what is that? It just extends to infinity, x equal to small. Is it correct? No, minus half. So it is just 2. The answer is 2. So this is finite. Therefore, f is in L2 of some right? But integral of mod f dx is integral of 1 to infinity dx by x to the power of 3 by 4. What is that? What happens to this? It becomes infinity because I have an x to the power of 1 by 4. So f does not belong here. So what we have now q, but not p. For p less than q we don't have. So in infinite measure spaces, belonging to higher LP does not mean it belongs to all the lower LP. And that's where the real major problem of Fourier transforms come. You can define the Fourier transforms of L1 functions much easily, but then you can't borrow this idea and say any finite energy signal or L2 function is in L1, therefore it's Fourier transform. No, if it's in L2 it need not be therefore. So all this big mess of approximations, etc., come into play. So the key to the crux of the matter is that in finite measure spaces, if P is less than Q, LQ implies LP. Whereas in infinite measure spaces, no such relation.
Okay.